Hello everyone. Welcome to the next lecture on the real analysis. Today we will see how we can learn the concept of the pointwise convergence of the sequence. Myself Dr. Harish. You can follow my YouTube channel where you can find the playlist of real analysis, and you can see that up to so far we have described the real analysis sequences. We have also defined the several results and also defined the infinite series results. In this complete playlist, you can see the sequence and series complete as well as the Taylor series, Maclaurin, all are available in this playlist. Now, as I told you in our previous lecture, we have defined and learned the concept of the sequence of the real number. That means if my sequence is xn, which is basically a mapping from the natural number to the R. Now, in this lecture, instead of the real number, we can define the sequence of the function like f and x. Make sure in the sequence of the real number, we have defined the sequences of the real number x n. However, in this case, we will learn how you can define the sequences in terms of the function. And sequence of the function is one of the most important topics in the real analysis, which can be used for obtaining the approximation of the given function. Once you can know the approximation of the given function, that you can use to define the new functions in the future task. So that's why the sequence of the function is one of the most important concept. Now, the objective of this lecture is we will learn how you can define the convergence called as the pointwise and uniform convergence of the sequence of the functions. So if you have the f of nx, then we will see whether it is a convergent pointwise and it is a convergent uniformly. And what is the difference between them, we will also see in this lecture. I hope you can like and comment on this video as well. The first basic difference between the pointwise and the uniform convergence is same as of the uniform convergent and the continuity. We all know that what is the difference between the continuity and uniform continuity. The same difference is appearing in the pointwise and uniform. Now, what is the definition of the pointwise convergence? What is the meaning of the convergence? Firstly, if you have the sequence of the function, say R to R, for example, fine, then the pointwise implies we will define the convergence of the Fn for each x, sorry, not for all, it's for the each x, for each x belongs to the R. That's the meaning of the pointwise convergence. That means we are talking about the pointwise convergence at each point of the domain. Mathematically, how you can define that? If you have the sequence of the function fn from a to r, then and I can say fn converges to the f, where f is another function from a to r, such that a is a subset of the r. Then you can say fn is convergence to the f pointwise if for every x belongs to the domain, if every x belongs to the domain, f of nx converges to the fx. What is the definition of the convergence? That is the limit as n approaches infinity, fnx is equal to fx. And that is the major definition you have to remember while solving the problems. Fine. So what is the definition of the pointwise convergence? If you prove that the sequence, if this limit is my finite, remember the limit must be finite, and that function is called as the pointwise convergent. Now, if you closely look about this function, the first question definitely arises is, if your given function fx is assumed that it's a continuous, or you may assume that this is a differentiable, or you may assume that it is a bounded, you may assume any of the other parts, then does the f also behave the same thing? That means if fn is my continuous, differentiable, bounded, etc., then does f also behave the same thing? The answer is not obvious. Fine. So let's investigate what is the behavior of the function fx when the function is continuous, differentiable, and bounded. So firstly, let's assume the first example. F of n is x square plus nx over n. So clearly say function is defined on the x. Fine. Now clearly say it is polynomial in x. Fine. It is a polynomial in x for the given n. So therefore, this function is my continuous for each x in the domain. So what is that domain is? Domain is my R. So function is continuous for the each x in my R. So therefore, the function is polynomial. So every polynomial is differentiable and continuous. Then what will be your target? Your target to check whether the f, what is the f is? If f of n converges to the f, does it also continuous and differentiable? How you can define the f? By the definition of the pointwise convergent, it is limit n approaches infinity of fn x. So your target is to firstly find the value of fx. So what is the value of the fx? It will be limit n approaches infinity x square plus nx divided by n. Fine. That is the definition. Now you can take n as a separate. Otherwise, it's a infinity by infinity form. You can apply the L'Hopital rule. Otherwise, you can take n as my separate. Fine. So as n approaches infinity, this value will be 0. Answer is x. Otherwise, because this is my infinity by infinity form, so you can apply the L'Hopital rule. It will be x square is a 0 plus with respect to n, it's a x over 1. So the answer is x. Fine. So therefore, you can see this is a finite limits. So therefore, my sequence of the function fn converges to the f pointwise. Fine. Now also you can see fx is my f. fx is my x for all x belongs to the R. Again, it is my polynomial. So therefore, f is my continuous. Every polynomial is continuous. F is my differentiable as well. Fine. So every function f is continuous as well as differentiable. Now, what does the meaning of this geometrically? That means if you draw the graph of this fx, if you draw the graph of this fn, that is my x square plus nx over n. What is the graph of this? If you take n is equal to 1, then this graph will be x square plus x. That's a parabola passing through the origin. This is my n is equal to 1. If you take n is equal to 5, then it will be my 5. Again, it's a parabola, but it has a wider length. Fine. And so on. You can see that this f1, that is the n is equal to 1. This is n is equal to 5 and so on. So, and if you take as n approaches infinity, the graph is my fx. And clearly say that f1, f5, f10, f20, if you take f of 100 and so on, the graph of the function fn will be flattened towards the line fx is equal to x. That's the meaning of the pointwise convergence. Now, this example shows that if fn is my continuous, then f is also my continuous. But does it true for all fnx? Does it true for all fnx? So the answer is not. Look at this example. So clearly say this is my polynomial. Fine. This is my polynomial. Again, function is my continuous as well. Then we can find gnx is my continuous. Then your first target is to find the pointwise convergent. That means your target is to find the limits of this thing. So what is the limit of this case? Or if you draw the graph of this, x is equal to 1 is a straight line, x is equal to 2 is a parabola, x cube, and then so on. Now, can you find the limit of this? So clearly say that domain is my closed interval 0, 1. I can choose the three cases when x is my endpoints or x is lies in between them. If x is 0, what is the limit? If x is 0, answer is 0. If x is 1, what will be the answer is limit 1. It is my 1. And if x is lies between 0 and 1, what is the limit of this case? It will be my 0. Fine. So the answer is when x is equal to 1 is a 0, otherwise x is equal to 1 is a 1, otherwise it is my 0. Now this is my fx. Fine. So this is my gx because it's my gn. So therefore gn converges to my g, where g is my this case. Now can you say that this function is my continuous? Is it continuous? No, this function is my discontinuous at x is equal to 1. So therefore, we can say the gx is not continuous at every point of this domain. Fine. So what is the investigation is, if fn is my continuous, does it behave the same? Not always. Fine. It is not always continuous. Now look at the second investigation. If I assume that fn is my differentiable, then does f is also differentiable? Let's see a simple example. I can define the function fn is, so clearly say fn is a polynomial. It's a under root of, we all know that under root of x is my differentiable function. Fine. So clearly say fn is my differentiable functions, and you can easily find the derivative of the function as x divided by x square plus 1 over n. Fine. Now, how you can find the fx? Again, you can take the limit as n approaches infinity of fnx. Now, since f is my complete R, so what is the limit of this as n approaches infinity? Can you find the limit of this case as n approaches infinity? So clearly say this quantity will be 0. The limit is my x square. So what is the root of the x square is? Mod of x. Fine. Now clearly say mod x is my not differentiable on the interval R. Fine. Or any interval which contains the point 0. But fnx is a convergent, is a pointwise convergent on this R, but it is not differentiable. So what you can say that the pointwise convergence does not preserve the differentiability. Look at one more example. If I define the hx, which are defined on the interval 0, 1, clearly say this is my polynomial, then it is my continuous as well as my differentiable as well. Then we can define, because the polynomial is a differentiable, we can define the pointwise convergent. Now since it has a closed interval, so it has the three cases when x is lies between x is minus 1, x is plus 1, or x is lies in between them. If x is equal to minus 1, so then this limit will be my minus 1 limit n approaches infinity minus 1 of 2n minus 1. When n approaches infinity, this part will be my 0. So the answer is minus 1. When x is equal to plus 1, the answer will be, this is my plus 1. This is 1 raised to power infinity. 1 raised to power 0 is plus 1. When x lies between minus 1 to plus 1, this part is again 0. Fine. So this number is lies between minus 1 to plus 1. So what is the answer of this? If you draw the graph, basically this number is my mod of x. So you can see the graph is mod x. Fine. Or if you want to draw the graphically, what will happen if you take n is equal to 1? So what is the graph of this? It's x raised to power 1 plus 1. That is a x square. So if you draw the graph, it's a x square from minus 1 to plus 1. Similarly, if you take x is equal to 2, x is equal to 3, and so on. So as I told you, this mod x is my not differentiable. And this the graph of this. This value is my fx, fn is equal to f1. Fine. Or you can call as the h1, because I have function is denoted by h. So h1. Fine. And so on. So this black color, this is my mode of x. So that is hx is my mode x. Clearly say the function this is my differentiable, but the function hx is my not differentiable. So what you conclude that if fn is my continuous, f may not be continuous. If f is differentiable, then h is may not be differentiable. Now let's see, investigate on the bounded case. So suppose fx is my function which I define on this case. Clearly say this function is my bounded. How? You can see, okay, firstly I can find the fx. Can you find the limit of this? Again, it's an open interval. What will happen if x is 0? Or you can simply say, there is no need to x is equal to 0. What will happen of the limit? As limit n approaches infinity of n over nx plus 1. Clearly say it's a infinity by infinity form. I can apply the L'Hopital rule. So that will be 1 over x. So the answer is 1 over x. Fine. Now clearly say this function is my bounded. Why? If you start from this part, what will happen? N over nx plus 1. Fine. Now, is it less than 1? Definitely. Why? Because we all know nx plus 1, whenever x lies between 0 to 1, this number is always less than equal to 1. So therefore, this number is always less than equal to n. Hence, fn is my bounded. Does this function is bounded? But this function is not bounded, because you can see whenever x is near to the 0, this function goes to the infinite. Or moreover, if you draw the graph of this 1 over x, this is the graph, and you can see this is my unbounded. Hence, if fn is my bounded, f need not be bounded, or you can say this does not preserve the boundedness. Next result is, if you prove that fn is my pointwise convergence, does their derivative also pointwise convergent? Again, we will see about the concept. Let's see. First example is fn. Can you find the fx? That is my limit n approaches infinity of fnx. So what is the limit of this case? Limit n approaches infinity of sin n over n. Clearly say it is infinity into a bounded function. Bounded function between -1 to +1. Sorry, 1 over infinity is my 0. So 0 into bounded function, the answer is 0. Fine. So that means fnx converges to the 0, or you can say fn converges to the 0. Fine. Now can we say, so what is your target? So can we say fn dash is convergent to the f dash? What is f dash is? 0. So for that, we firstly need to compute the derivative of the fnx. So with respect to x, what is the derivative with respect to x? N cos nx over n. So that is my cos nx. Fine. Now we can compute its limit. So limit fn dash x as n approaches infinity. I call this number is f dash. So what is the limit of this quantity as n approaches infinity? Cos of nx. So the number is lies between -1 to 1. That means limit not exist, because it is not unique. So that means the limit does not exist. What does it implies? Fn dash does not converges to the f dash pointwise, because the limit does not exist. So we can see in general the function is not differentiable pointwise convergence. So what you have obtained is, if the function is continuous, sequence of the function is continuous, then the pointwise may or may not be continuous. If the function is differentiable, the function is may not be differentiable. Similarly for the bounded. So the answer is, it is not always necessary. Now the big question arises is, if fn converges to the f pointwise, fine, then what condition or what hypothesis you have to impose, so that if fn is my continuous, f must be continuous. If fn is my differentiable, f must be differentiable. If fn is my bounded, then f must be my bounded. Fine. So what concept or what additional thing you have to include so that this property will be satisfied? So that's a major question arises in the real analysis, and that answer will be provided you by the uniform convergence. Fine. But before I can directly move on the uniform convergence, let me do some more examples on the pointwise convergence so that you can understand this concept easily. Look at this case. Now examine the pointwise convergence. What will be your target in the pointwise convergence? Your target is to find the limit of fnx. Fine. So where fn is my this case. Now can you find the limit of the fnx? So definitely, what is the domain of this case? Domain is my R. And clearly say from this case, if x is my 0, answer is 0. And if x is my non-zero, answer is my non-zero. That means you have the two different cases. So if x is my 0, what is my fnx? Fnx is my 0. If f is non-zero, what is my fnx? So that is my nx over 1 plus n square x square. Now once fnx is my 0, can you find the limit of the fnx? It is also 0. Fine. So I call this limit is my fx. Fine. Now if f is non-zero, can you find the limit of this? So clearly say it is infinity by infinity form. I can apply the L'Hopital rule with respect to n. So it's x over 2nx square. So clearly say when n approaches infinity, this limit will goes to the 0. This is the first method. How you can find the second limit? Second method for compute the limit. Limit n approaches infinity. I can divide it numerator and denominator by n square. So this limit is my here. Fine. Can you find the limit as n approaches infinity? 0, 0 plus x square. So the answer is 0 because x is my non-zero. Fine. If x is my non-zero, the answer will be 0. Fine. So what is my fx? If I call this number is my fx, so what is the obtained value of the fx? It is 0 if x is equal to 0, and if x is non-zero, it is again 0. So what you can say that means f of x is my 0 for all x in my domain of R. Fine. So therefore fnx converges to the 0 pointwise. Fine. So examine the pointwise convergence. Yes, it is a pointwise convergent and it converges to the 0. Now look at the another example. Show that the sequence this is pointwise convergence on the closed interval. Again, your target is to find this case. If I call this number is my fx, then your target is to find the limit. So clearly say now they are talking about the closed interval. I can compute the values at x is equal to 0. I can compute the value at x is equal to 1. And I can compute the values lies in between them. Fine. So what is the value of the fx, fnx when x is equal to 0? First case. When x is equal to 0, answer is 0. What is the value of the fnx when x is equal to 1? Again 0. Fine. So if this part is 0, what is the limit n approaches infinity of the fnx? It is also 0. Fine. So the limit of the fnx is my 0 for the case when x is equal to 0, x is equal to 1. So remember that my target is to find the three cases: x is 0, x is 1, and x lies between 0 and 1. So when x is 0, fx is my 0, f1 is my 0. Fine. Now the case is when x lies between 0 and 1. What is my fnx? It is nx 1 minus x raised to power n. So can you find the limit of this? So what will happen if you take the limit is infinity? 1 minus x, because x is lies between 0 and 1. This number is also lies between 0 and 1. So 0 and 1 raised to power infinity is my 0. So that is indeterminate form. Fine. So how you can solve that? So once it's the indeterminate form, I can write into the infinity by infinity form. Fine. How you can make them as an infinity by infinity form? I can write this quantity as minus n. Now clearly say this limit is my 0 by 0 form. Once this limit is my 0 by 0 form, can you apply the L'Hopital rule with respect to n? It is my x. What is the derivative of the a raised to power x? A raised to power x log of a. So 1 minus x raised to power minus n into log of 1 minus x into derivative of minus 1 minus n is of minus this quantity. Now since we have taken the limit with respect to n, so the numerator x is a common, denominator is minus common, log of 1 minus x common. Then the limit n approaches infinity, I can take on this bracket in the numerator. Now clearly say 1 minus x is lies between 0 and 1. Now if you take as infinity, the answer will be 0. Fine. So that will be minus x into log of 1 minus x into 0. Now again you can see that this is the case when x is lies between 0 and 1. This quantity is my non-zero. This quantity is non-zero. So complete answer is my 0. Fine. So what you conclude that in both the cases, that means if x is my 0, the limit is 0. If x is 1, the limit is 0. And if x is lies in between 0 and 1, answer is again 0. So we can say the function fn converges to the 0 for all x in my domain. Hence, Fn converges to the 0 point. So this is a simple way you can understand about the concept of the pointwise convergence. Make sure, student, the most important thing is if Fn converges to the F and this is my continuous, then this may not be continuous, may or may not be continuous. Fine. If this is my differentiable, then again this may or may not be. If this is my bounded, this may or may not be. So we will see the next lecture more example on the pointwise convergence so that you can understand it more deeply. Till then, you can like and comment on this video. You can share this video with your friends. Happy learning always, and don't forget to subscribe my YouTube channel. Best of luck, students. Thanks for this support.